This video will cover the two methods of charging an object known as conduction and induction. Both of these two methods are primarily used with charging a conductor. We'll discuss at the end what can be done with an insulator. The first method we'll cover is charging by conduction. With charging by conduction, you need at least two objects. Both must be conductors. At least one of the two objects must be initially charged, either positively or negatively. The two objects I'll demonstrate with are this green block and this blue sphere. If you were to count the charges on each, you'll notice that the green square is neutral, meaning that it has the same number of positives and negatives. And the blue circle is positive, meaning that it has more positive charges than negative charges. Charging by conduction can also be thought of as charging by contact, because to charge something by conduction, the two conductors must make contact with each other. Let's watch what happens when they make contact. I'll bring the circle in contact with the square. And now, these both being conductors, we've provided a space that the electrons in the square are really attracted to, because opposite charges are attracted to each other. So some of the electrons will leave the square and will travel into my circle here. Just how many depends on the charge of my circle. Specifically, these two objects should end up with the same charge. If even more electrons were to go into my circle, then all of a sudden they'd be more attracted to the square than the circle, because my square has now become positive since it has lost electrons. Notice that I moved two electrons, or two negative charges, into the circle. That's because my circle was initially a +4 charge, and now that I've moved two negative charges, both my square and my circle have a +2 charge. I can now separate my two conductors, and both of them are left with a +2 charge. Let's see what happens when one of my objects is initially negatively charged instead of positively charged. Once again, my square is neutral, but my circle has more negatives than positives. Specifically, there are 8 negatives and 4 positives, so we say that the circle has a -4 charge. Once again, I have to bring them in contact with each other. And when I do that, these negatives, they're all repelled from each other because like charges repel. So some of them will travel into my circle. When I say some, I specifically mean 2 of them. Because if 2 of them transfer, then my circle is left with a -2 charge, and my square has a -2 charge. Some of these charges may also distribute themselves around the circle so that they're evenly spaced, or approximately evenly spaced. Now that all my charges have transferred, I can separate my two objects, and I now have two conductors, each with a -2 charge. Charging by conduction means charging through contact with two conductors. Charging through induction is a bit more complicated. Charging by induction is a method for charging a conductor, which means the object that you want to charge must be a conductor. It can start off neutral or it can start off charged. Either is fine. Once again, you must start with another object that's initially charged, but with induction, the other object, the circle in this case, does not need to be a conductor. So my circle could possibly be an insulator. When you charge by induction, there is no contact between your two objects. So that means that this circle will not contact the square. Instead, it'll just come nearby. You'll notice that my circle is positively charged. Well, looking at my conductor, This is started off neutral, but the negative charges are attracted to the positives in the circle. They can't get there because they can't leap through the air, but they can move within the square so that they are closer to that circle. Now, of course, not all of them are going to move super close because they are repelled from each other. But there is a general movement of these negative charges so that they are, in general, closer to this circle. So the first step in charging by induction is to move a charged object near but not touching the object that you wish to charge. As a result, the charges will move inside the conductor. The next step in charging by induction is to ground my conductor. Grounding means that you provide a path from your conductor to the ground. The ground is considered to be an infinite acceptor of electrons or an infinite source of electrons. The ground could be anything. It doesn't have to be the physical earth. Really, the ground is any large object that may have multiple charges in it. So you can ground something by touching it and connecting it to your body. Your body is large enough that it can take on or give up several electrons. The symbol for grounding is 3 lines. The top line being the longest of the 3, the second line being the middle in length, and the last line being very short. They kind of make a triangle. When you connect something to ground, you do so usually with a wire or some other conductor. So to show that I am grounding this object, I will use a wire to connect the object to that grounding symbol. I mentioned the ground is an infinite source or infinite acceptor of charges, specifically electrons. In this case, electrons will want to come up from the ground into my conductor because they're attracted to this positively charged object over here. So some electrons will travel up from the ground through that wire into my object. You don't need to worry about how many travel in this case. It's a bit more complicated than with conduction. Once this square is happy with being charged, your next step is to remove the ground. It's very important that you do this prior to removing the initially charged circle. Removing the ground just means disconnecting it. Nothing really happens as a result of that. But then I'm allowed to remove my initially charged object, and as a result, these negative charges will all spread out again, approximately evenly, depending on your object. I'm now left with a negatively charged object that was initially neutral in this case. Notice that the object that I used was positively charged, but I ended up with a negatively charged object. That's different than conduction. Let's see the process one more time, this time with initially negatively charged object. So my first step is to take my initially negatively charged object and bring it near but not touching my conductor. As a result, the electrons will move. Notice that in all of these times we haven't been talking about the positive charges moving. That's because the positive charges, or protons, are fixed in the nucleus and don't have the freedom to move, unlike the free electrons that are in conductors. This time the electrons move to the left because they're repelled from my negatively charged circle. My next step is to ground my conductor. Again, just providing a path from the ground to my conductor. And as a result, some of these electrons will leave my conductor. Leaving my conductor into the ground means they're getting further away from this negatively charged object, and they want to be as far away as possible. But once again, not everything will leave, because if everything left, Well, we'd be left with something that's really positive. And these charges really like those positives too. So just a few will leave. The next step is to remove the grounding wire. And then finally, we can remove my initially charged object. And these negative charges will once again spread out. We're left with a positively charged conductor, and we did so using a negatively charged object. Now, both times that I've been going through this process, I've mentioned that it's really important that you remove the ground before you move the initially charged object. Well, what would happen if we didn't? In other words, what happens if I leave this connected to ground and I move this out of the way? Well, in that case, there's nothing keeping these electrons over to the side there. So they're going to spread back out. And I've got a nice positively charged object. Well, these electrons that are in the ground, they're attracted to that positively charged object. So they're going to travel right back up into my object. Now I don't end up charging the object at all. It ends up being neutral in the end, which is not what I want. So it's very important to remove the ground before you move this initially charged object. Now, both of these two methods, conduction and induction, are methods for charging a conductor. But we all know that sometimes you can charge something that's an insulator, such as a rubber balloon. That's a little bit more complicated. Without getting too much into the chemistry, when you're charging an insulator, you typically do so by rubbing it. Rubbing causes friction. Friction causes heat, and heat breaks some bonds of the molecules and atoms inside your insulator, therefore making that spot that you rubbed charged. So there's a little bit of charge transfer between the object you're rubbing and the material you're using to rub it with. Once again, it's not conduction or induction. It's a little bit more complicated of a process. One thing that is unique when you charge when you charge an insulator, is that the object as a whole does not become charged, just the place where you rubbed, where you broke bonds. The last thing we'll discuss in this video is not a method of charging, but rather a process of separating charges. This method explains what happens when a balloon sticks to a wall, or when sometimes your hair becomes staticky, or things of that nature. To fully understand the process, I have a little demonstrator here. Notice that I have a balloon, and my balloon starts off neutral, as most things like to be. My balloon, being an insulator, can pick up charge through rubbing. So I'm going to rub my balloon on this nice wool sweater that's just hanging here. And notice that as I rub the balloon is picking up some negative charges. Notice also that when I let go of the balloon, it's attracted now to my positive sweater. We know that opposites attract, so that makes sense. However, if I bring the balloon close to the wall, the balloon is also attracted to the wall. And that's something a little bit different, because my wall's not charged. Now, if you take a look as to what happens as I bring the balloon slowly toward the wall, you'll see that those negatives are shifting over a bit. That's because they're repelled from the negative that's in the balloons. But again, not conductors, so there's no transfer of charge here. Instead, the negatives are just shifting over a little bit so that one portion of the wall becomes positive, and thus the positive attracts the negative of the balloon. So we're going to look at that simulation one more time. Starting off, I have a negative object here. When I bring it near my neutral object, the neutral object could be anything, it doesn't have to be a wall. The negative charges in the atoms shift a bit to the right because they're repelled from the negative of the object here. As they shift to the right, one side becomes positive and one side becomes negative, and therefore it's attracted. If I do something similar with a positively charged object, the negatives would shift in the opposite direction, being attracted. So notice that the negative charges don't actually leave the atoms themselves. It's just as those electrons are circling the nucleus, they spend a bit more time on one side than on the other. That's how polarization works.